Hi guys, I am on page 25 of your new BC review packet that you received today to go through the model free response problem on page 25. Follow along with me and make sure that you're taking notes in your packet so that when we meet for tutorials tomorrow, you can ask me questions and we can go over anything that you didn't understand. I apologize for the quality of the video. I'm outside, so it's a little windy. Turn your volume up if you need to. Here we go though. We have a sequence here defined as 1 over n times the log of n for values of n greater than or equal to 3. In part A, we're given the function defined as 1 over x log x, and for x is greater than 3, we're told f is continuous, decreasing, and positive. Use the integral test to show that our series diverges. So if you'll think back to our conversations on series, these three characteristics right here should sound pretty familiar: continuous, decreasing, and positive. Those are the conditions that we have to show in order to be able to use the integral test. So since the College Board is giving us those characteristics and telling us to use the integral test, it's no mystery. We just have to go right in. And the integral test is supposed to show that the integral from 3 to infinity, that's my starter and my ender up here on my sigma, of 1 over x log x, this integral is going to behave just like our series. So if the integral diverges, the series diverges. If the integral converges, the series converges. So I just need to do some integration, which hopefully isn't horrible based on what we've been going over lately. I'll let the limit as r approaches infinity guide me here with this improper integral of 1 over x log x with respect to x. Something that many of you overlooked on your quiz that we're going to definitely need on this problem is a u substitution using log x. Du then is 1 over x dx. If I isolate dx, I'll multiply and get that dx is equal to x du. So it's to return to my integral and replace two things, the u and the differential. So in this example, this becomes for me the limit as r approaches infinity of the integral from 3 to r of 1 over x times u times x du. The great thing about that is that my x's cancel, and the integral that's remaining is of 1 over u, and I'm pretty confident about 1 over u resulting in the log of u, and I'll go ahead and return that u in with our log x so that I can run this from 3 to r, and I'll remember to tack my limit on at the front. So thankfully this isn't horrible. Now I can go in with my upper bound. That's going to be the log of r minus the log of 3, and we're going to let that r value approach infinity. So this is the limit as r approaches infinity of the log of something big called r minus the log of 3. I definitely get a finite value over here at the end, but we know enough about our parent functions to remember that the log of infinity approaches a y value of infinity. So this is an infinite limit, which means that my integral diverges and therefore my series diverges too. So somewhere at the end here, you can just write a quick statement that shows that the series, I'm not going to put everything here, but of 1 over n log n diverges by the integral test. And sorry, I'm out of room here, but you get the idea. Forgive my bad handwriting. Okay, now we're in part B. We're asked to consider the infinite series that alternates and captures that series we were looking at before, 1 over n log n. We want to identify properties of the series that guarantee that the series converges and explain why the sum of the series is less than 1/3. So in order to show that this converges, I need to be reminded now, since my terms are alternating, about the alternating series test. This one required us to show three things. We want to show that our series is positive, decreasing, and has a limit as n approaches infinity of 0. So if I can show these three things, then I'm going to be able to verify that this series converges utilizing the alternate series test. So the positive and decreasing terms, I'm supposed to just look at the magnitude or the absolute value of the expression here. So kind of remove the alternating layer. And if I just look at those terms, the positive terms of this, I've got 1 over 3 log 3, 1 over 4 log 4, 1 over 5 log 5, and I can see here for sure that my terms are positive. And I can also capture that the denominators are growing in size, which means the fractions are decreasing in size. So I got my first two items marked off the list. Sometimes you'll see that they say the absolute value of our sequence is positive and decreasing and goes to 0. What I want to show now is the goes to 0 part. So I'll look at the limit as n goes to infinity of 1 over n log n. This is most definitely bigger in the bottom, so that goes to 0. And I can say that we converge by the alternating series test, and we're all good. Okay, and finally here on part C, we're asked to just find the interval of convergence for a power series and show the analysis that leads to our answer. So to find an interval of convergence, we're going to always use the ratio test. This is a great problem because it's reviewed us on 3 of our Big 10 tests here. Sorry y'all, it's so windy. And the ratio test, remember, is the limit as n goes to infinity of the absolute value of the next term, so that's x minus 2 to the n plus 1 over n plus 1 times the log of n plus 1 divided by our current term, or in this case we'll just multiply by the reciprocal of our current term to go ahead and clean this stuff up. So the great news is that algebraically some of these exponentials cancel themselves out for us. Specifically, if I have, oh shoot guys, sorry, I made a mistake right here. I needed the next term on this initial numerator. So the original term is n plus 1. That means the next term is n plus 2. Sorry, I missed that the first round. I noticed because I wanted to cancel here and I knew I was going to have an x minus 2 left over somewhere. With that mistake in the power, I was going to run into some issues. Now that I've fixed the power, I've got x minus 2 to the n plus 2 all over x minus 2 to the n plus 1. This whole term down here is gone, and I'm left with a single x minus 2 up in my numerator. And if you're not remembering where that's coming from, side note, x minus 2 to the n plus 2 is the same as x minus 2 to the n times x minus 2 squared. And in the bottom, I've got the x minus 2 to the n plus 1. So that's the same as x minus 2 to the n times x minus 2 to the 1. When it's written like this, you can see a little bit more clearly how a lot of this stuff cancels out and leaves me with just a single x minus 2 on top. Anyway, that means I can come down here, take out anything with an x, because our limit is actually asking us what happens as n's get bigger, not as x's get bigger. That leaves me with n log n over n plus 1 log n plus 1. Thankfully, I'm pretty familiar with my growth rates here, and the fact that these two numerator and denominator terms are growing at the same rate means this entire limit is equal to 1. So what I have is the absolute value of x minus 2 times 1. Remember, I'm looking for an interval of convergence. The ratio test, it shows that we converge if our limit is less than 1. I can break this down now, dropping the absolute value bars into this inequality, which leads me to add 2 to every side to a basic interval from 1 to 3. Now, the only thing left is for me to conclude if I should in fact leave those inequalities as is, or if I need to include either endpoint. So I'm going to start fresh now and test my endpoints. And, sorry, I had the highlighter on. I'm going to say, let's let x equals 1. That means this summation actually becomes 1 minus 2 to the n plus 1, or negative 1 to the n plus 1, over n log n. This is alternating again, so we just showed in the previous problem that this converges by the alternating series test. I don't need to re-show that. I did all that a second ago, which means my inequality that I had built or started to build is most definitely going to include the endpoint at 1. I want to also verify what's happening at 3. That means my summation, 3 minus 2 to the n plus 1, becomes 1 to the n plus 1 over n log n. If I rewrite just a tiny bit, 1 to any power is 1. So this is really the sequence inside of that sum. Well, this looks familiar too. I think I showed in part A that this diverges by the integral test. Again, I don't need to show all my work again, but that's a huge conclusion because that means that I should not include the other endpoint and I'm actually done with my work. So that was a pretty intense free response, and after this in your packet, I can show you, all I have coming up here is the practice multiple choice questions. There's no official check for understanding here. So what I need everybody to do, there's like quite a few multiple choice questions, but I want you to focus on 1, 2, and 3 on page 26. These are the 3 that I'm going to check as your pre-work for tomorrow. Question 1 is a nice assessment of your rules and your tests. So I would consider things like the nth term test, comparison tests. Those are good to attempt. You want to try and find one series that converges. Question 2 kind of threw me for a little bit of a loop. So I want you to go back to your notes and see if you can find the expansions for e to the x, cosine of x, and sine of x. We had memorized some Maclaurin expansions for those functions. And if you have access to those, this one actually isn't nearly as scary. Question 3 is also kind of a nice assessment of your p-series, and I want you to try and uncover what power would generate 2 divergent integrals. So those are the only 3 I need you to attempt for me tomorrow. We'll score first thing in tutorials, and I will see you then.